Hello everybody, my full name is Abdusattar Jamshidbek and my group name is Eka English IT. Today I will be talking about the quantum internet. My presentation topic is quantum internet. This presentation is made for the subject Computer Systems Organization and Architecture by the Professor Patrick Smorevs. In the first slides, as you can see, this is our presentation topic, quantum internet and quantum key distribution, QKD in short. In the next slides, we will be talking about a table of contents. As you can see, here's a table of contents which defines the longevity, the information we will be talking about in the following slides. First of all, what is the quantum internet and principles of quantum mechanics relevant to networking? Quantum key distribution, QKD, how QKD works, BB84 protocol, types of QKD systems, current states, real-world implementations, and challenges, limitations, and future of the quantum internet. We'll be talking about all of that in the next slides. And the third slide, as you can see, we will be answering the question, what is a quantum internet? Quantum internet is a next generation communication network that uses quantum mechanical phenomena such as superposition and entanglement to transmit information with fundamentally different properties than classical networks. As you can see, quantum physics uses superposition, entanglement, no-cloning theorem, and teleportation. All in all, superposition. Quantum bits, in short, qubits, can exist in multiple states simultaneously, enabling richer encoding of information. Entanglement. What is entanglement? It means two entangled particles share a correlated quantum state, regardless of the distance separating them. No-cloning theorem. Unknown quantum states cannot be perfectly copied, making eavesdropping detectable by any design. Teleportation, as everybody knows. Quantum state transfers not matter is possible between modes using entanglement and classical channels, which is, in other words, teleportation. Quantum mechanics principles in networking. How are we able to use quantum physics in networking, in communication, online communication? Qubits. Qubits is a basic unit of quantum information. Unlike classical bits such as 0 or 1, qubits can be in a superposition, 0 and 1 simultaneously. Quantum entanglement. Two or more particles become correlated, such as measuring one instantly determines the state of the other, even across the vast distances. And also there's Heisenberg uncertainty. It is a theory in quantum internet. It is possible to measure certain properties simultaneously with arbitrary precision, fundamental to QKD security. Quantum measurement. Observing a quantum system collapses its superposition into a different state. Any eavesdropper inevitably disturbs the transmitted data. And also the last thing, photon polarization. Photons can be polarized in specific orientations, basic states. QKD encodes key bits into photon polarization angles. In the next slide, as you can see, quantum key distribution, how QKD is distributed, how quantum photons are distributed. Definition: QKD is a cryptographic method that uses quantum mechanics to securely distribute encryption keys between two parties. Any encryption attempts is detectable due to the laws of quantum physics. In other words, why QKD matters. Unconditional security information theoretic non-computational, immune to quantum computer attacks. Eavesdropping changes the quantum state, always detectable. It stays always detectable. and enables future-proof encrypted communications. And also in this slide I put a table which shows quantum. In terms of safety, quantum physics is not considered very safe, but the key exchange between classical photons and QKD is RSADH, and photon channel eavesdrop detects. In terms of classical and in terms of QKD, it's passive. In terms of QKD, it's always active. And how QKD works: the WB84 protocol, developed by Charles Bennett Giles Prescott in 1984, the world's first QKD protocol. Alice Alice prepares photons. For example, Alice randomly selects bits and bases and sends polarized photons to Bob, and then Bob measures. Bob randomly picks a measurement basis for each received photon. His results match approximately 50% of the time when bases align. Basic reconciliation: Alice and Bob publicly compare which bases they used, not the bits. They keep only results where bases matched, and then they will do error check. A sample of shared bits is compared. If error rate is below threshold and no eavesdropper is present, privacy amplification. Remaining bits are processed with hash functions to shorten the key and remove any potential particle information if obtained. And the final stage is secure key ready. The final shifted key is used as a one-time pad for perfectly secure communication. And also there are types of QKD systems. First prepare and measure PM protocol WB84 B92. Alice prepares quantum states and sends them to Bob. I'm sorry for the police noise. Bob measures with a randomly chosen basis, simpler to implement, most commercially deployed. Entanglement based protocol E91. A source creates entangled photon pairs and distributes them to Alice and Bob. Security is derived from Bell inequality violations. Suitable for satellite-based QKD. Continuous variable. Uses quadratures of the electromagnetic field amplitude phase instead of single photons. Compatible with standard telecom infrastructure. And also the last thing is measurement device independent, removes vulnerabilities in the measurement apparatus. Both parties send quantum states to an untrusted relay, higher security against detector side channel attacks. And our last slide is about current state, real world implementations, and the challenges, limitations we have for now, and I believe it will soon be improved by the modernization of technology and AI. Nowadays in China, in Mr. Satellite, world's first quantum satellite was launched, created, put into use. It was 2016 demonstrated satellite to ground QKD over 1,200 km. Beijing and Shanghai 2,000 km quantum backbone network operational. Europe. E-Quantum Communication Infrastructure Initiative aims to build a continent-wide QKD network by 2027, integrating fiber and satellite links. In the USA, there's a quantum DOE Quantum Network. US Department of Energy operates 17-node quantum network. NIST is leading QKD standardization efforts alongside post-quantum cryptography. Commercial ID Quantic, Toshiba. ID Quantic, Switzerland, and Toshiba offer commercial QKD system. Tokyo QKD network has been operational since 2010 for almost 16 years. In the last there's challenges, the future of quantum internet, key challenges, of course, distance limitations. Distance is the biggest challenge for individuals, for users of quantum internet for these days. Photon loss in fiber 100 to 100 kilometers. Quantum repeaters still largely experimental. High cost of equipment and single photon detectors. High cost of tools. Standardization and interoperability between vendor systems. Vulnerability to side channel attacks on physical hardware. And in terms of future outlook, quantum repeaters enable long-distance quantum networks by storing and retransmitting qubits. Quantum memory store quantum states for synchronization across network nodes. Satellite plus fiber hybrid secure global quantum internet by 2030s. Post-quantum plus QKD hybrid approach. Deploy both QKD and post-quantum algorithms for maximum security. And the last slide, I put the sources that I took the information from, the data from, the data I used it in this presentation of mine. So I also put my full name and the professor's name, Patrick Moreves, and the group name, ECA English IT. In the below of every slide. So it's end of my presentation. Thank you very much for your attention.